Marhaba. Okay, in this session we want just to have examples of countable sets. Okay, remember a set is called countable, a countable set if it's either finite or countably infinite. And remember, so S, say countable set, means that the cardinality of the natural numbers is equal to the set S. This is the meaning of countably infinite. Okay, and cardinalities are equal means there is a bijection, so there exists a bijection f from n to s, which means if you have a bijection f from n to s, it means that we can list all elements of S in an infinite list. Okay, so let's have an example of a countable set. For example, if S is the set containing 5, 7, 13 and 99, then this is countable because it is a finite set and the cardinality of S is 4. It has 4 elements. Okay, so this is one example of a countable set. It's a finite set. Okay, let's have another more interesting example of a countable set. So the set of natural numbers is countable. Why it is countable? Because it is countably infinite. Okay, countably infinite. Why it is countably infinite? Because there is a bijection. From, so there is a bijection from n to itself, and this bijection, one example of at least one bijection, the easiest one is the identity function. So this is iota from n to n, which sends iota of n is equal to n. So iota of 0 is 0, iota of 1 is 1, iota of 2 is 2, and so on. So you can check that this is injective and surjective. Okay, another way to see that n is countably infinite is because we can list its elements. So 0, 1, 2, 3, 4, and so on. We can list the elements of n, and so it is countably infinite, which means it is countable. Again, a set is countable if it's either finite or countably infinite. N is countably infinite because there is a bijection with itself, and so it's countable. Okay, let's have a more interesting example now. So example, let D be the set of positive odd integers. Okay, the question is, show that D is countable. Show that D is countable. Okay, how do you show that a set is countable? You have either to show it's finite or it's countably infinite. Clearly, the set of positive odd integers, okay, is not finite. They run forever. So this means we need to show that D is countably infinite. So in other words, show that D is countably infinite, which means that we need to show that the cardinality of the natural numbers is equal to the cardinality of D, which means there's a bijection from n to D. And if there's a bijection from the natural numbers to D, we've seen that it means that we can list the elements of D. So one way to show that D is countably infinite is by listing its elements. Can you list the elements of D? Yes, we can. The first positive odd integer is 1, the second is 3, then 5, then 7, then 9, and so on. Since we can list the elements of the positive odd integers of D, we can list all of them. So choose any odd integer, say 33, it will appear at some point here, and the list continues. So since we can list all of them, then this means that D is countably infinite, which means that it is countable. Now, this is a quick solution for the question, but if you want a very detailed solution, then we need to show this, that the cardinality of N is equal to the cardinality of D. Okay, which means that we will give a bijection from N to D. So we want a bijection F, say, from N to D to show that D is countably infinite. Okay, this shows that D is countably infinite. Right? This is how we define countably infinite, that D is countably infinite if the cardinality of D is equal to the cardinality of N, and two cardinalities are equal means there is a bijection from the first set to the second set. Let's try to find this bijection. Okay, let me list the elements of the domain. What are the elements of the domain? They are the natural numbers. And what are the elements of D? They are the positive odd integers. So 1, 3, 5, 7, 9, and so on. Now, I hope that this listing of the natural numbers and the odd integers will give you a hint of what is to find the formula for the bijection. Okay, so let's suggest that the function f will take a natural number n and its image will be what? You see 0 is mapped to 1, 1 is mapped to 3, 2 is mapped to 4. I see that it is twice the input plus 1. So twice n plus 1. So this is the function, okay, from f, from the natural numbers to D, that we nominate to be the bijection. Okay, so we remember we need a bijection. Okay, right. For example, f of 4 is 9. 2 times 4 is 8 plus 1 is 9. We want to show that this function is a bijection. Okay, let me say this again, that if D is countably infinite means there is a bijection from N to D. So there is at least one bijection. I don't say every function from N to D is a bijection. I'm saying there is one, and I'm giving an example of one, which is this one. But now I want to really show that it's a bijection. So first, we will show that F is injective. How do you show that F is injective? So let M and N be in the domain. Choose any two elements in the domain and suppose they have the same image. So suppose they have the same image, then we want to show that these 2 points are actually the same point. So if they have the same image, then what is the image of M? It is 2m plus 1. And what's the image of N? It's 2n plus 1. But if we subtract 1 from both sides, then this is 2m is equal to 2n, and then divide by 2, this means m is equal to n. Okay, this shows that this function is injective, right? Because what we showed now, if you choose any two elements in the domain and they have the same image, they turned out to be the same element. Okay, this shows injectivity. And second, we want to show surjectivity. F is surjective. Okay, how do you show F is surjective? It means that if you choose any element in the codomain, remember this is the domain, the natural numbers, and this is D, the set of positive integers. If you choose any element here, what is its pre-image? Okay, you see how do we obtain the pre-image? We subtract 1 from the element we choose in the codomain and divide by 2. So let's say n be any element in D, which is the set of positive odd integers in this question. So we need, so this is n and this is D, and we chose n here. We need to find some pre-image m whose image is n. This is the surjectivity. Every element in the codomain has at least one pre-image. Okay, we've seen that. Okay, take m to be n minus 1. Look, since n is odd, then n minus 1 is even, and so when we divide by 2, we get a positive, non-negative whole number. So this means that n minus 1 over 2 is indeed an element of the natural numbers, because it's either 0 or positive, and it's a whole number, because n minus 1, so let me write that n minus 1 is even. Okay, now take this m. We claim that m is a pre-image. Let's check that m is the pre-image of n. So f of m is what is f of m? It is 2. What is the function f? It takes an input, multiplies it by 2, and add 1. So the image of m is 2m plus 1. But what was m? M was n minus 1 over 2 plus 1, and this means this is n minus 1 plus 1, and n minus 1 plus 1 is n. So indeed m is the pre-image of n. So we showed that f is surjective and f is injective, which means we found at least one bijection from n to d, which is the function which takes a natural number and maps it to its double plus 1. Okay, so this shows, so therefore, so since f from the natural numbers to d is as defined above is a bijection, we know that d is countably infinite, and so d is countable. So this is another example of a countable set, which is the set of positive odd integers. But intuitively speaking, d is countable means we can list the positive odd integers. Again, we can list them: 1, 3, 5, 7, 9, 11, 13, and so on. This means that d, the positive odd integers, is a countable set. Okay. Okay, let's have another example on countable sets. Okay. So, example, show that z, the set of integers, is countable. Okay, again, z is not finite, so this means to show it's countable, we need to show it's countably infinite. And to show a set is countably infinite, this means we have a bijection from the natural numbers to the set. In other words, we can list the elements of the set. Okay, remember, what are the integers? What is this set? This is the set of all negative whole numbers, 0, and the positive whole numbers. Okay, this is the set. Now the question is, can we find, we want to show z is countably infinite, which means we need to find at least one bijection. Can we find a bijection? Let's call it f, from the natural numbers to the integers. Okay, so which means what? So these are the elements of the natural numbers: 5, 6, and so on. Okay, and the question is, what should be the images of this function? What is the image of 0, the image of 1, the image of 2, such that we will get a bijection? Which means, what does it mean for f to be a bijection? That here we can, it has to be surjective, right? Which means that the range is equal to the codomain. The codomain is equal to z, which means the images must contain all z, all the elements of Z, all positive, negative, and 0 whole numbers. And we also shouldn't assign two elements here to the same image. So in other words, can you list the elements of Z? So, okay, let's start. What do you want the image of 0 to be? Let's say 0. Okay, what do you want the image of 1 to be? Again, we need to choose one which a new one. Okay, otherwise it will not be injected. Say 1. What will be the image of 2? Okay, if you want to continue like this, 2 and 3 and 4 and so on, there's a problem with this, because okay, clearly it's injective function, but it's not surjective, because the range of this function is not all the codomain, right? No negative numbers are appearing as images, so we need to think harder, and we need, while we are listing, to list the negative numbers as well. So this means that here I want to assign -1 to be the image of 2. Okay, now since we listed 1, let's list 2, and since we listed 2, let's list the -2. And now again we list here 3 and -3. Okay, and we continue like this. So if this is 7, this is 8, then the image of 7 will be 4, the image of 8 will be -4, and now you see the pattern. So this is clearly a bijection from the natural numbers to the integers. Why? Because see, every two elements in the domain have different images, and it's surjective, which means all of the set here appears, every element in the set is the image of some element. Okay, so what is the pattern here? How? And notice again, since F is a bijection, this means we can list the elements of Z. Look here. So how do we list all integers? By saying 0, 1, -1, 2, -2, 3, -3, 4, -4, and this list will list all the integers. Since we managed to list all the integers, in other words, we have a bijection from N to Z. This means that, so thus this shows that Z is a bijection. Sorry, Z is countably infinite. Is countably infinite. And why Z is countably infinite, the set of integers? Because there is a bijection from N to Z, or in other words, we can list the elements of Z in an infinite list. Okay, and so Z is countable. Okay, this shows that Z, the set of integers, is countable. Okay, notice that what we did is that since we found the bijection from N to Z, right? What does this mean? This means that the cardinality of N is equal to the cardinality of Z, right? Because this is how we define two sets to have the same cardinality. If there is a bijection from the first to the second, look, this is the picture. Every element in N has a one and only one partner in Z, and vice versa. Every element in Z has one and only one partner in the natural numbers. Okay, maybe this is counterintuitive, but what we are saying here, that the amount of natural numbers is the same as the amount of the integers. Both are infinite sets, and here we established that the quantity of the natural numbers, or the size of the natural numbers, is the same as the quantity of the integers, because there is a one-to-one correspondence. There is a bijection from the natural numbers to the set of integers, because look, your fingers on both hands are equal, because you can find a bijection. And this is what we did here between natural numbers and Z. The 0 is partnered with 0, 1 with 1, 2 with -1, 3 with 2, 4 with -2, and so on. So every element in the natural number, it has a partner and only one partner, and every integer has one and only one partner in n. This shows these two sets have the same size.